So, hello everyone. My name is Jinchen Shi, and I'm a third-year PhD student in Rutgers University, and I'm now working with Dr. Drew Hadley. So, my research interests focus on computational neuroscience and more specifically in dendritic computation and how the computation in a single neuron or a single dendritic branch can help us understand the circuit computation. So today I will give you a brief introduction to the polynomial regression models, which is widely used in neuroscience data analysis. So let's we start. So we have learned about the linear regression before. So its form look like this. So we have some input x represent either direction or different features, and we have some neural response or output represent as y. So theta y is the slope or the ratio between the input between x and y, and the theta 0 is the intercept. So if we fit the relationship between x and y, it will look like this. So it's linear. But sometimes the relationship between our input and x and output on your resource y is not that simple. It could be complicated. So in this case, we can use some updated version of this linear regression to add some slight change to this equation. So which will be the polynomial regression. So in that case, let's say we have some relation between our x and y. You look at this. So if we still use a linear regression, so it may not be sufficient. You can see this field result is not quite well. But we can use some, let's say, the polynomial regression with the power to 2 and refit the relation between x and y, so it will look great. So that's why sometimes we may use the polynomial regression in neuroscience data analysis. So like in linear regression, we will also structure a design matrix for this polynomial regression. So the basic form for this polynomial regression looks like this. We have shown in the previous slides, and then we can rewrite it in the vector form for the data point I. So we can say the yi equals the theta I times the xi. So theta and theta I and xi here are both vectors. So it represents different variable parameters in the form, and the si represent the different s value with different powers. So s0 with the power of 0, so it's just 1, xi and si with the power of 2. So further, we can build up this vector form for different data points y and to a matrix version. So it looks like this general form y just equals s times theta. So remember here, so the vector y is the y0, 1y, 1, 2 is different scalar value. But here the s0, sy, s2 is different vector, which is shown in the second row. So it's a vector, it's not a scalar value. And the same for the theta 0, theta I, and theta 1 and theta 2 is also a theta vector, is not a scalar value. So here, this matrix for this x value is a design matrix we want to build for the polynomial regression, just like linear regression. So here I will provide you a simple code exercise to structure design matrix by yourself. So here's the code. So basically, this function will get two input, the input vector x and the order we want. Let's say we want to process a polynomial regression with the order with 2. So I will give an example input. Let's say we have the input x equals 1, 2, 3. That's a vector. And the order 3, we want to go up to the polynomial relationship between x and y with 3. So let's go over the code to see what can we get. So first, in the first step, since our number of dimension of our x vector is 1, so we will add a new dimension to this vector to make it to become a matrix, because we want to get a design matrix for a vector, right? And in the second step, we will calculate the first column for the design matrix, which will be the power of 0 for different x value. So it's just 1. And here the s shaper 0 will just be the number of the values in our x vector. So it will be 3. So what we will get in the first step will just be 1, 1, 1 for each row. And then we'll call a for loop to calculate the different columns in this design matrix. So the second column in the matrix will be the power of 1 for different x value, which will just be the original value. So it's 1, 2, 3. And third column will be the power of 2 for different x value. So 1 times 1, that's 1. 2 times 2 times 4. And 3 times 3, that's 9. And finally, the last column will be just power of 3 for different x values. So it's 1, 8, and 27. So, and then we'll stat the different these matrices at yeah, let me see. Yeah, Yeah, the horizontal direction, because we want different rows in this design matrix to represent different power for the same x value. So let's see what result can we get here. So we can see the first row in the design matrix represent different power for the x value, the first x value 1. So x value, so we can see is the power with 0, 1, 2, 3 for x value 1. And the second row is different power for the x value 2. And the third row will be the at different power 0, 1, 2, 3 for the x value 3. So basically that's it. Thank you.